Problem 2. Electrons in a magnetic field. A beam of electrons emitted by a point source P enters the magnetic field vector B of a toroidal coil, toroid, in the direction of the lines of force. The angle of the aperture of the beam 2 by alpha 0 is assumed to be small, 2 by alpha 0 much less than 1. The injection of the electrons occurs on the mean radius r of the toroid with acceleration voltage v0. Neglect any interaction between the electrons. The magnitude of vector B, is assumed to be constant. Question 1. To guide the electron in the toroidal field, a homogeneous magnetic deflection field vector B1 is required. Calculate B1 for an electron moving on a circular orbit of radius r in the torus. Question 2. Determine the value of vector B which gives for focusing points separated by pi over 2 as indicated in the diagram. Note, when considering the electron paths you may disregard the curvature of the magnetic field. Question 3. The electron beam cannot stay in the toroid without a deflection field B1, but will leave it, with a systematic motion, drift, perpendicular to the plane of the toroid. Part A. Show that the radial deviation of the electrons from the injection radius is finite. Part B. Determine the direction of the drift velocity. Note, the angle of aperture of the electron beam can be neglected. Use the laws of conservation of energy and of angular momentum. Given data, charge E over mass m is 1.76 by 10 power 11 coulomb by kilogram, V0 equals 3 kilovolt, R equals 50 millimeters. Question 1. To guide the electron in the toroidal field, a homogeneous magnetic deflection field vector B1 is required. Calculate B1 for an electron moving on a circular orbit of radius r in the torus. Solution to the question 1, determination of B. The vector of the velocity of any electron is divided into components parallel with and perpendicular to the magnetic field B. Formula 1. The Lorentz force F equals negative E multiplied by cross product V. B influences only the perpendicular component. It acts as a radial force as in equation 2. Hence the radius of the circular path that has been traveled is in equation 3, and the period of rotation which is independent of V perpendicular is in formula 4. The parallel component of the velocity does not vary. Because of alpha 0 much less than 1, it is approximately equal for all electrons to V0. Expression 5, hence the distance B between the focusing points. Using equation 5, is in formula 6, B approximately equal V0t. From the law of conservation of energy follows the relation between the acceleration, voltage V0 and the velocity V0. Equation 7. Using equation 7 4 1 obtains from equation 6 B equal expression 8, and because of B equal 2 pi r over 4 1 obtains magnetic field B equal expression 9. That was solution to the question 1. Question 2. Determine the value of vector B which gives for focusing points separated by pi over 2 as indicated in the diagram. Note, when considering the electron paths you may disregard the curvature of the magnetic field.
Determination of B1. Analogous to equation 2 we have expression 10. From equation 7 follows magnetic field B1 equal to expression 11. That was solution for question 2.
Question 3. The electron beam cannot stay in the toroid without a deflection field B1, but will leave it, with a systematic motion, drift, perpendicular to the plane of the toroid. Part A. Show that the radial deviation of the electrons from the injection radius is finite. Question 3. Finiteness of R1 and direction of the drift velocity. In the magnetic field, the lines of force are circles with their centers on the symmetry axis, z-axis of the toroid. In accordance with the symmetry of the problem, polar coordinates r and phi are introduced into the plane perpendicular to the z-axis, see figure below, and the occurring vector quantities, velocity, magnetic field B, Lorentz force, are divided into the corresponding components. Since the angle of aperture of the beam can be neglected, examine a single electron injected tangentially into the toroid with velocity v0 on radius big R. In a static magnetic field, the kinetic energy is conserved, thus E equal 12. The radial points of inversion of the electron are defined by the condition v r equals 0. Using equation 12, one obtains expression 13. Such an inversion point is obviously given by small r equal vector big R in cylindric coordinates v phi equal v0, v r equals 0 and v z equals 0. To find further inversion points and thus the maximum radial deviation of the electron, the components of velocity v phi and v z in equation 13 have to be expressed by the radius. V phi will be determined by the law of conservation of angular momentum. The Lorentz force obviously has no component in the phi direction, parallel to the magnetic field. Therefore it cannot produce a torque around the z-axis. From this follows that the z component of the angular momentum is a constant. It means Lz equal mv phi small r equal mv0 big R, and, therefore v phi equal v0 multiplied by big R over small r, equation 14. Vz will be determined from the equation of motion in the z direction. The z component of the Lorentz force is Fz equal negative E big B v R. Thus the acceleration in the z direction is az equal expression 15. That means, since b is assumed to be constant, a change of vz is related to a change of r as follows: delta vz equal negative E over m by b delta r. Because of delta r equals small r minus big R and delta vz equals vz1 finds vz equal expression 16. Using equations 14 and 15 from equation 13, we have dependency 17, where A equal E over m by big R over v0. Part B. Determine the direction of the drift velocity. Note, the angle of aperture of the electron beam can be neglected. Use the laws of conservation of energy and of angular momentum. Discussion of the curve of the right side of equation 17 gives the qualitative result shown in the following diagram. Hence R1 is finite. Since big R less or equal small r, which is less 0. R equal R1, equation 16 yields Vz less than 0. Hence the drift is in the direction of the negative z-axis.